to introduce us as our second speaker for the day. Tennessee Leeuwenburg is a data scientist and software developer with over 20 years of experience. He has an interest in open source software, machine learning, and forecast verification. His current research work includes the development of scientific machine learning models for weather and environmental prediction. Verifying, evaluating, and interpreting complex data really requires specialist tools and methods. This talk, he's going to introduce Scores, an open source Python package for verifying and evaluating scientific results from labeled multidimensional data of any scale. Scores includes over 50 metrics, statistical techniques, and data processing tools. Please welcome Tennessee.
Thank you very much, Genevieve, and thanks to PyCon AU for having me. I'll start with just an acknowledgement of the fact that all open source development is a team effort, and I'd just like to acknowledge the contributions of the team, all of the team members that have contributed to its development. So, what is Scores? Scores is a Python package, great start, has been mathematical functions. So for people who are familiar with stats packages, it might be similar to statistics packages that you've used in its sort of general nature. And one of its main claims to fame is the support for labelled n-dimensional, multi-dimensional data, which is used in many scientific fields and in machine learning. Scores should work well on any data for which xarray can be used. At present, it's primarily supporting the geoscience communities, but there's really no reason it should be limited to those fields. So let's put ourselves in the mindset of verifying a prediction in this case. So I've chosen weather examples for two reasons. One, it's familiar to me from my work, and the other one is that all of you have most likely experienced weather at some point in your life. So it should be familiar to interpret. So a straightforward example of something that is easy to understand whether it is good or bad is a prediction saying it's going to rain on Wednesday, and if the outcome is that it does not rain on Wednesday, that is not a good forecast. It is less clear if the prediction is that it will be 17 degrees and it turns out to be 19 degrees, and it is particularly fuzzy if someone says there will be a 25% chance of a thunderstorm and then there is not one. So questions asked in verification, it's often common to say, it's common to frame these things in the negative, to be honest. A lot of people say, is it incorrect? How wrong? What is the error? But I've tried to frame these questions in the positive. Is it perfect? Is everything about it perfect? Usually in a stochastic situation, not everything about a model will be perfect. And we rapidly progress to, is it reasonable? And a lot of the functionality in Scores is based on the assessment of whether or not something is reasonable. Is it within an acceptable tolerance? Is Model A better than Model B? How many issues per year should we expect if we adopt a particular model? Does it work when we really need the model to perform well? Also, what kinds of problems are there? Is it too fast? Is it too slow? Is there too much or not enough? And is it in the right place? Scores is designed to help address these challenges. It's very well documented. There's a Jupyter Notebook tutorial for every metric. It works with labelled n-dimensional array, as mentioned earlier, handles missing data, not a numbers, weighting, masking, and a variety of other aspects and characteristics and nuances as well. And it uses Dask for scaling and performance, so it's equally as comfortable on a laptop or a supercomputer. We have 100% automated test coverage plus manual testing, and the code for every metric has been reviewed by at least one scientist and at least one software developer. Here's a sampler of the kinds of metrics that you might find in Scores. In general, I'm not going to talk to kind of like every single point on the slides. I just like having the reference material up there if people want to take a look or if someone's watching a video later and wants to push pause, etc. So a quick primer on data structures. I imagine this will be familiar territory for most of the people here. So tabular data is any data that's in a table structure. Think spreadsheets, think pandas. Pandas is very good for tabular data. There are alternatives, and it's a great library, but things start to get a little woolly when you have complex multi-indexes. N-dimensional data may technically have any number of dimensions, including the number of dimensions you find in tabular data, but it's most commonly used to refer to data with 3 or more dimensions. NumPy is very commonly used for this. Xarray is also a great choice, and it's the one that we've made. Labeled n-dimensional data is where that n-dimensional data structure carries with it a label on the data structure for each of the dimensions that it contains. And that's where we're headed to today. Scores primarily works in this fashion, and we'll see why that's useful shortly. This table provides, for people wanting a bit of an example of each of those different sort of dimensionality aspects, something that might be helpful in visualizing the kind of data that we're talking about. Weather model data in particular is very often quite high dimensional, and it starts to be useful to think more about coordinates than indexes. So they're often quite complex coordinate aspects to the data, and then multiple variables that are indexed by those coordinates. Now, this was in case the sides got chopped off my slides. So let's talk about reducing and preserving dimensions. So people are used to thinking of something like mean absolute error as a number, like 0.4 is a good example of mean absolute error, but it can also be a map or a graph. In this case here, we use scores to compare the difference measured by mean absolute error between the initial conditions of a model and the predicted surface temperature over the next 10 days of lead time. The left of these two images collapses or reduces the time dimension, but preserves latitude and longitude, giving you a map of where the errors and differences are most likely to occur. The image on the bottom right of the two images does something different. It collapses, reduces the latitude and longitude, and instead preserves the time dimension, so that you can see how this varies with respect to the diurnal cycle over the days and over the lead times. This comes from the tutorial we provide on working with mean absolute error, which includes downloading realistic data to make it available. Just in case it's not visible on the big screen, that's the bit we're talking about with reducing the dimensions. Each of our scores and metrics allows you to pass in the dimensional preservation and reduction arguments, allowing you to do this kind of dimensional exploration with respect to the error characteristics that you're interested in. And if you don't specify either, everything gets reduced and you get the number. Another way to interrogate the data is using weighting. Global weather models have lower levels of accuracy at the poles due to the collapse of the spacing between the grid points around the poles, and the geographic area is representing a smaller physical area in each case. As a result, errors that are near the poles are going to have an outsized effect in a physical sense. So area weighting by latitude is very effective at reducing the outsized impacts of these errors in order to get a more realistic picture of how error is varying in real terms. This kind of weighting can be used in any number of ways, but that's one reasonable example. Now, if we proceed to consider the same question over Australia. So if we consider the image on my far right, we see here a population density map of Australia and an area which includes the surrounding ocean. If we perform the same latitude weighting that we performed in the first example, not a lot changes. There are actually differences between those two charts, but they may not be obvious on the presentation. If instead we weight by population density, our errors turn out to be almost zero everywhere, because statistically speaking, the population density is almost zero everywhere. So all of your errors just get washed out. Finally, if we mask that, so we can use the weighting also as a mask, and focus on where the population density is greater than zero, we weight it by population density, then we start to get a picture of how the forecast accuracy starts to affect people. And that's a way that we can use our data interrogation to understand the impact of our forecasts on people. That's not to say these other areas, which don't have people, as many, statistically as many people, are unimportant. It's just a different question. So it allows you to focus your question go beyond a generic metric to focus the results on a question of interest. And that's a theme we'll see again and again. There is no one silver bullet verification number that can be used to fully understand the performance of a model, which certainly is challenging in the context of machine learning, which has a single target optimization function. There are a number of other areas where basic methods can underperform, where scores can help. One of these circumstances is rare events. So J.P. Finley in 1884 started making predictions of tornadoes. It's all right, predicting tornadoes is much more accurate now. What this is a fantastic statistical sample data set that's very well known in the field. So there are almost never tornadoes considered in aggregate. So if we take a look at Finley's forecasts, he predicts for the tornadoes at a rate of 3.6% or 0.036 roughly. And we're going to compare it here to a very simple model which always predicts no tornado. So if we take a look at the accuracy of Finley's model, it is 96.6% accuracy. I think that a lot of people would assume that it's a very good model. That sounds like a high level of accuracy. If we compare it to our alternative model, which always says no tornado, we find that that is 98.1% accurate. Which of these two is more useful? If we go in and look at the false alarm ratio, we see that Finley's predictions are more often wrong than right. However, we see if we use the no tornado model, there is no solution to the false alarm ratio because you end up with a div by zero error and not a number. If we use the threat score, that is considering the times when tornadoes were either forecast or observed, then we start to see the usefulness of Finley's predictions. It may be what would be statistically called a weak predictor, but there is value in it. So you could pay attention, and if you had, for example, an extremely low cost response to the possibility of a tornado, I'm not a tornado expert, this may not be a very sensible example, but suppose it was as simple as parking a car in the garage, you probably should do so. You can still get value from the model. Another area where basic methods can underperform is extreme events and risk. They can require special handling in a number of ways. So I'm going to pause for a moment. A prediction can be made by either a model or a person. In the weather forecasting context, it's a mix of both. There are models that estimate the state of the atmosphere and make predictions about the weather, but there are also people who are in the loop, forecasters or operational meteorologists, who are providing a supervised approach to the forecasts that go out. But there would be circumstances where there would be no model, and there would be circumstances where there would be no people. People can be potentially inclined to over-predict an extreme event because they don't want to miss out on something significant or have people under-respond to a significant upcoming event. Alternatively, in theory, they could under-predict them so as not to be seen to be exaggerating. So it's important to understand how to assess someone's performance in these contexts. Predictions can be made at various likelihood thresholds. So another kind of spin on this sort of extreme event question is like, well, how bad can it be? So instead of asking the model to produce its estimated mean state or even a spread, it's like, please give me a realistic expression of the worst case. In those circumstances, where you are predicting a worst case or a particular percentile, say the 90th percentile, you can't reasonably evaluate that with something like root mean squared error, which is proportionate to the mean expected value, or mean absolute error, which is consistent with the median expected value. Neither one of those is consistent with the prediction of a 90th percentile value. Scores contains families of consistent scores, which do allow the evaluation of forecasts that occur at these different thresholds, allowing people to make a proper quantified expression of what they mean when they're predicting an extreme event and be assessed accordingly and proportionately. Another area where there's often great interest is in sensitive receivers. Sensitive receivers isn't really a weather term, but it's one that I came across which I think is quite apt. And that's where, if we look at the graph on the bottom, that's where someone is particularly affected by the thing that you're forecasting in an unusual way. So an example might be if your backyard can cope with a certain amount of rainfall, but above that amount, it starts to affect your backyard and you might have some localised localized flooding and you need to make sure to unclog your drains before the rainfall occurs. That might be a sort of simple example. Or other people might have an issue with it being too hot, or other people might have an issue with a particular part of the range, such as around if it was temperature 0 Celsius, where freezing occurs and people may be particularly sensitive. So these so-called threshold weighted scores allow you to combine a consistent score with the thresholds of interest in a way that's mathematically fair for evaluating the model. So in this example, the area under the curve represents what we're going to accumulate for the score. The green and the purple, I'm slightly colourblind, if I've got those colours wrong, forgive me, represent two alternative forecast models that we could choose from to provide to our sensitive receiver who's expressed their preferences through the graph on the bottom. And visually, it's not kind of immediately clear which one is going to be best. The forecast 2 is generally below the green line through most of the range, but the green line has this sort of sudden drop off at the high end of the range, so maybe a value at the high end. And in this case, that's what we see. Forecast 1, which is in green, has the better threshold weighted mean squared error. So we have a range of threshold weighted metrics that allow you to explore questions of this kind. We have the following, these are tables of data. Here we have the following continuous scores, the following probabilistic scores, the following categorical scores, the following spatial scores and statistical tests. I'd like to wrap up by discussing how you can potentially get involved. So we have been an open source first package in the way that we've conducted this work. Much of the code has its origin in earlier software development that the team undertook at work. But from the outset, we've set this up to be something that people can contribute to, highlight the documentation. I'll be particularly interested to hear from people from other disciplines. We have issues on the GitHub tracker ranging from quick and easy to more involved. And some of the scores team will be around for the sprints. And I think I've finished in good time to take questions. Thank you.
Are there any questions from the audience? Tennessee, just while we're waiting for people to have a mic run to them, I'm wondering if you have advice for people who might be getting started with a package like Scores and know that they have a particular type of data, so they know it's continuous or categorical, and are trying to figure out how they're going to choose the best metrics or the best approach from the really wide array of options that are available. How do you think people should go ahead with getting started?
Sure, it's a pretty I feel like that's going to be very different by what field you're in.
Fair enough.
So there is, like, it would be very useful if we had like that kind of quick kind of guide to how to go and select them. I think the easiest ones from my perspective to get started with are actually the kind of continuous scores, because most people would be fairly familiar with them. I would suggest following from there to some of the threshold weighted scores feel to me like the most powerful way to assess these things in the end, but I think there's a pathway through some of the other scores to get there. Also, the categorical scores, also be binary contingency tables or contingency table metrics would be other names that people know them by. Also have like a really strong kind of intuitive sense, things like the false alarm rate or the skill score, or some of these other examples here are reasonably easy to communicate to other people, so I'd concentrate on the ones that are easy to communicate to people.
Yeah, that makes a lot of sense. I also noticed that you do have a number of tutorials available in the documentation, so that seems like a really fantastic resource. So do we have questions from the audience? It's a bit difficult for me to see, so if you have one, chuck your arm straight up. Great.
Yes, thanks for a great presentation. I assume you do, but I was wondering if you could give an example of scores that are used to evaluate errors where, like in forecasting, for example, your metric is shifted in time or in space, but the kind of shape is still correct?
Yeah, so we do, It's a really interesting area because if your forecast is off in terms of timing, telling the difference between a spatial error and a timing error can be difficult because a timing error of a feature that's moving will often be exhibited in a single time slice as a spatial error, so they're a little hard to discriminate. The most difficult thing about that is the double penalty problem, because you forecast it where it isn't and you've missed it where it is at the same time, so that's what makes it sort of difficult to properly represent that with something that's like a mean squared error. The fraction skill score is one approach to that, so-called, some people would call it like a neighbourhood method, which is where you kind of use a sliding window style approach to look at the number of pixels in overlapping areas that share the same characteristics. But it's also an evolving area in terms of metrics. So I think that's where verification science itself is still moving forward.
Thank you. Is there any other questions from the audience? We have time for a few more. Just see everyone heading up there now.
Can you hear me? Oh,
yes.
Wonderful. Thank you for the great talk. I was really interested in the sensitive receiver example you were showing there. Is that thresholding weighted function you've got at the bottom there, is it open-ended what you can put into that? Like, does it have to be monotonic, or can it potentially sort of come down again?
There's an underlying driver called the consistent score. So if you wish to pass an arbitrary function into and you're confident you know how to do that, you can do that. There are a couple of different included kind of standard patterns. This is called trapezoidal weighting. The other one is a step function, and it can be double-ended. So it doesn't, in this case, there's a sort of a single step, but it can define a range. So there's a couple of more accessible API calls for those simple weighting functions, but you can get in there and provide, any response that you want.
Wonderful, thank you.
Thank you. Adam, do we have any other questions from the audience?
Yep. Hey, thank you very much for the awesome talk. I certainly feel like if I've got a good understanding of the package, there's plenty of sort of useful metrics that people can sort of use to interrogate the data. But I think even the first question sort of indicates often finding the metric that you want is quite difficult. And just going off the idea you suggested a second ago, which is it'd be nice if there was kind of something that kind of guides around. I feel a bit gross being the first person to use this word here, but LLMs I'm fairly cynical about, but I think one thing they do pretty well is actually guide people to information in situations where getting the information wrong is sort of pretty low consequence. So in sort of have you considered using sort of that technology to kind of let people have more natural conversations about sort of finding the right metrics that might suit their particular application, obviously with something that's a little bit more guided than your generic LLMs?
Yeah, it's a lovely idea. So I think it could be plausible. There'd be so the direct answer is no, we haven't explored it. I think the main reasons from our perspective are obviously the focus is on constructing the methods, but also in terms of our ability to kind of like host and explore those things, we really are kind of limited to the traditional sort of website arrangement at this point in time. I think it'd be really interesting, those sorts of guided knowledge exploration ideas, but at the same time we want to be like the information that's in there in the tutorials and the documentation, we're trying to be sort of fairly authoritative. Like every score's got a citation for where the metric has come from and how it's been derived in terms of its mathematical origins. So I think it could help, I think your concept could help people, but it's a little less clear to me how we'd proceed on it.
Great. Any other questions? Everyone's had a chance? Well, in that case, I'd like to present you, Tennessee, with this speaker gift. We have a PyCon Australia mug included inside. We also have a sticker and a badge. Lots of fun stuff there. Everybody, if you could please welcome me in thanking our speaker, Tennessee Leeuwenburg.
Thank you very much.